So the first presentation today is coming from me. This is a talk that's kind of, well, it's focused on gprMax obviously, but it's a bit more kind of technical around the sort of performance and speed of models that you might want to run, and the various different ways that we have looked at the performance of gprMax and how to improve it, and how to really kind of make use of the hardware developments in computing that are kind of constantly going on. So let me just switch to my slides. There we go. So, I mean, why do we care about you know, how fast our simulations run? Well, you know, at the end of the day, the faster something runs, the faster we can hopefully get some results, and the faster we can, you know, get on with our research. So, you know, we always want things to run, our simulations to run as quickly as possible. And actually, access to, you know, higher performance computing machines and graphics cards, as I'll talk about shortly, is becoming a little bit more easy and more commonplace. So, you know, where once an HPC might have only been available, you know, to a few universities, now, you know, almost every university has an HPC, and even, you know, companies of different sizes have small clusters or workstations available to them. So kind of access to larger amounts of compute power is definitely becoming more common and easier. And on top of that, you know, we have things like cloud compute, which is kind of another direction that is making it a bit more accessible. However, you know, although we have access to bigger and faster resources, we're always coming up with bigger, more complex, more challenging simulations to run on them. And, you know, that still means that a lot of the models that we create, where we want them to be as real as possible, are still, you know, big 3D models that can require significant resources. And the other direction that kind of certain areas of our research is going in, and we'll hear a bit more on this from Iraklis later today, is towards using a lot more artificial intelligence and machine learning. And for that type of research, if you want to kind of create a robust machine learning system, often you're talking about training that model with hundreds or thousands of simulations. So when you're having to run that volume of models, then obviously performance is a big factor. So I'm going to kind of dive straight into some specifics. So if you remember back to day one, we created a really simple 2D model, initially taking an A scan of a metal cylinder buried in a half space. And then once we'd done that, we kind of moved on and looked at creating a B scan of the same model, which basically just involved rerunning that model 60 times. And for each model run, we moved our source and receiver along the surface of the half space to build up our B scan. Now, the reason I'm kind of bringing us back to that model is that I want to discuss an option in gprMax that can help where you have a model that contains a simple source and receiver. So where you're using a theoretical source such as a Hertzian dipole, the only thing that's changing in your model when we run it to create this B scan is the position of the source and the receiver. None of the actual geometry, the rest of the geometry in the model is changing. That's all fixed. You know, the half space is staying the same, the cylinder is staying the same, etc. So in those types of scenarios, what you can do to improve the speed of your model is you can use this argument called geometry fixed. And what that basically does is it means that gprMax doesn't reprocess any of the geometry information between these different A scans. So why does that improve performance? Well, often what you'll find is the building stage of the model. So the stage in which gprMax basically interprets all of your geometry and material commands and then builds up the FDTD grid. Depending on the type and the size of model that you have, that stage can take some time. And if you're running a B scan without this geometry fixed argument, then for every run of the model, you're having to rebuild that geometry. And as I say, if that's quite a time-intensive process, then doing that 60 times can add up to a significant chunk of time. So by using the geometry fixed argument, gprMax basically builds that geometry once for the first A scan, and then just reuses it for all of the other model runs. And the only thing it changes in those model runs is the position of the source and receiver. So as I say, that can improve the performance of your model if that build stage is particularly time intensive, if it takes quite a long time to do that. So I'm gonna do a quick demo of this just to show you how it works. In this particular case, actually the build time for such a 2D model is fairly insignificant anyway, so we're not really going to save a great amount of time using this option for this example, but at least it's going to show you how it works. So let's just go back and take a look at the input file that we're going to use. So here it is here. So as I say, this is what we created on day one. It's a fairly straightforward model, and it contains a couple of commands, source steps and receiver steps, that are there to move the source and the receiver. So if we jump into gprMax, and we just run this without the geometry fixed command to see what that looks like again. I won't run, it's not A scan, B scan. We won't run all 60 of them, but if we start this going, then you see actually, this is a fairly quick 2D model anyway. So it doesn't take that long actually to build it or run it for that matter. But, you can see on my screen there, every time we create another A scan, you can see all of the text that's printing out to show that the model is being rebuilt every time we do that. So I'll just let this finish actually, since it's quite quick. What we'll then do is run exactly the same thing with the geometry fixed argument. Let me just clear up the screen. So same model now with geometry fixed. And now you basically see that every time we create a new A scan as part of our B scan, we don't reprocess the geometry. So like I said, this is a fairly small model anyway, so the time saving here is not particularly significant. It's just designed to demonstrate how you would use this, but for models where that build time is fairly significant, and you're creating a B scan, then this can be quite a useful command to use. Yeah, so you can see in this case, I think we've probably saved, about 10%. I think the last total time to complete was around sort of 44, 45 seconds, something like that. Now, just before I move on, the other thing that you can do, obviously, as I said, the geometry fixed really only is applicable if you're using a theoretical source. So, you know, what happens if you're using an antenna model? Well, you can't use the geometry fixed command in that case, because if you think about it, between each of your model runs, you're having to move the geometry and structure of the antenna. So your entire geometry of the model is not fixed. But you do have some other options to speed up the build time. What you can do basically is you can save all of your geometry that does not include the antenna model and dump that to file. And then you can load that back in on each of your model runs then. So instead of gprMax having to build the rest of the geometry, it can just load it in from file. It can add your antenna model, which will be, you know, relatively quick, and then it can run it. So that's another kind of option or tip you have where you're using an antenna model and you want to save a little bit on the build time. And the commands to do that are called geometry objects write and geometry objects read. And you can have a look, you know, at how to use those in more detail in the manual. So I wanted to kind of just give a very brief overview of CPU and GPU computing to kind of explain why we're able to get so much performance by moving to computing on a GPU. And this is quite a kind of a simplistic overview of the two here. But in essence, you know, your laptop or workstation these days will have, you know, a handful or more of CPU cores. And the CPU cores are basically designed to handle very generic tasks. So, you know, they need to be able to cope with, you know, copying files, reading email, browsing the web, all sorts of different tasks. And additionally, you know, I said before, our kind of access to high performance computing has improved. High performance computers has improved, but they are still, you know, very expensive to design, build, and run. And certainly the larger ones are still, you know, you're still only going to get access to them through a research center or a university. Or some kind of nationally provided system. So, you know, they are still expensive. On the other hand, a GPU now contains thousands of cores, and each of these cores is designed to handle much more specific task, and that's basically what we're going to exploit: the number of these cores. And the ability to work in step to do a specific task. And when you look at the cost performance benefit that you get from a GPU for these types of models, as we'll see in the next few slides, it really is a very beneficial route to follow. So in gprMax we have several kind of options for performance in terms of CPU and GPU parallelization. On the left-hand side, these are the kind of technologies that we use for parallelizing code on the CPU side. So by default, gprMax uses OpenMP, which is a shared memory threaded programming model. And you know, that will take advantage of multiple cores on your laptop or desktop machine, or you know, it will scale up to many more cores on a single node of an HPC. So that will happen by default, and you know, you'll see that in some of the messages that are printed when you use gprMax. The other thing we use on the CPU side is MPI. Which is designed for distributed memory machines. There are various different ways in which you can use MPI. At the moment, we basically use MPI to kind of distribute models or distribute tasks across large HPC machines. So the other way of using MPI, or one of the other ways of using MPI, is to basically decompose a model that is extremely large into different parts, and then run each of those parts in parallel on a different node of an HPC machine. So we don't do that yet. That's something that we're looking at for the future. But again, that needs some kind of software resource and time to make that happen. So on the GPU side of things, our solver can use NVIDIA's CUDA framework to run on NVIDIA GPUs. And actually we use a toolbox called PyCUDA, which allows us to basically write Python and access the CUDA API to do that. So that makes that quite neat and ties up well with the rest of gprMax. And another kind of framework that we're working on at the moment is the use of OpenCL, which is much more platform agnostic. So you can use OpenCL on a variety of CPUs and GPUs from different manufacturers. So it's a bit more flexible than CUDA in that respect. But what we have seen is that the performance is not quite as good. So we plan to still work on bringing OpenCL to gprMax, but it's not top of the priority list at the moment. So FDTD is really attractive to parallelize because basically for each time step you can update the electric and magnetic field components completely independently. So you can utilize, for example, these thousands of cores on a GPU, and each of them can be updating a separate field component. And that's basically what you see from this is one of the FDTD update equations for the electric field. You basically can see that it depends upon previous values stored in memory of the electric field and of surrounding magnetic field components. And the immediately surrounding thing is important as well, because that basically means that you're not having, or rather the code is not having to look for previously stored values in memory that might be far apart in terms of the location in memory. And when you start doing things like that, then the performance can drop off quite quickly. So I want to look at specific performance now, and this graph basically looks at the OpenMP performance of gprMax. So this is based on the CPU. And this is performance based on an Intel Xeon workstation machine. You can see the dotted black line is basically linear scaling. So we've got speed up factor on the y-axis and then number of CPU cores or threads on the x-axis. And then the various traces basically represent different model sizes, different number of cells. So what we see is obviously we don't get linear scaling. We weren't really expecting that, to be honest. But what we do see is as the number of cores increases beyond sort of 4 to 8 threads, the speed off starts to kind of tail off and flatten a bit. It happens more for the smaller models than the larger ones. That's basically because for the smaller models, the kind of overhead associated with setting up all of these threads has a larger impact than the compute needed for that size of model. So basically, when you have larger models that take longer to run, it's more worthwhile, using more threads, because that overhead becomes a smaller percentage. But you can see for the 300 and 400 cube models that the performance is pretty much starting to converge. So that's kind of the best we can do on the CPU side with a fairly decent workstation. If we have a look at a slightly different performance metric, this P basically is a measure of the number of millions of cells per second that we can compute, and P is based on basically the dimensions of your model in X, N, Y, and Z, the number of time steps NT, and the total solving time for your simulation T. So the chart on this slide basically looks at a few different workstations ranging from kind of a decent desktop workstation with 4 gigahertz i7 cores, which is the green bar, and then looking at more kind of workstation class CPUs and CPUs that you might find on the node of an HPC. So, I mean, one of the takeaways from this, if you look at the sort of 400 and 500 cubed domains, we see that the performance begins to kind of saturate at around 400, 420 million cells per second for the 20 core machine. So how about GPU performance? We worked on a project with Google, and as part of that, they wanted us to develop a CUDA-based GPU solver. And having done that, we then were able to test the solver on a range of different consumer and data center spec NVIDIA GPUs. And what we found through our testing basically is that the gprMax and the FDTD algorithm are basically constrained by what we call memory bandwidth, and the memory bandwidth of the GPU. So I'm not going to go into kind of details on that, but the takeaway there is if you're considering running gprMax on a GPU, you want to look at the memory bandwidth figure for that GPU and try and pick the one with the maximum memory bandwidth. The other thing about GPUs that we kind of touched on yesterday, and probably the biggest drawback, is the RAM size. When this slide was written, the current maximum RAM size on a GPU was about 12 gigabytes. That has changed and is changing quite quickly now, and we're seeing GPUs with 24 and 48 gigabytes of RAM. So that allows you to run much bigger models on GPUs. So let's take a look at the performance of some different GPUs versus our kind of best case CPU scenario. So the orange bar from the previous slide of our 20 core HPC node has now become the green bar on this slide. And then we have basically a range of consumer and HPC spec GPUs. So the consumer GPUs would be kind of regarded as the GeForce cards. Titan is a little bit more than that, and then the Tesla cards are basically the kind of high-end HPC spec cards. But what you see immediately is even for the consumer spec cards, the performance compared to a 20 core CPU workstation is much more. We're seeing a 15 times speed up in many cases versus the 20 core machine. And if you were to put the 4 core desktop machine on this plot, then you'd see speed ups of around 50 times. Obviously, that depends also on the complexity of your model. If you start introducing lots of dispersive materials and such like, then the performance will drop off. But you can see from that in terms of computing for gprMax, GPUs are most definitely the way forward in terms of performance. So I'm kind of running out of time a little bit, so I'm just going to skip this demo for now. What I wanted to just quickly mention, and I touched on it before, is some work we've started to do developing an OpenCL version. And that work came about through our participation in Google Summer of Code last year. So we had funding for a couple of students. One of them was John, who worked on the subgridding that we talked about yesterday, and the other was Manish, who worked on developing the OpenCL acceleration. So we haven't done a lot of kind of benchmarking on this yet, but this is a graph that kind of compares the sort of 20-core CPU for performance to OpenCL on a couple of different graphics cards and versus CUDA that I just showed you on one graphics card. So CUDA still wins. It's still faster than OpenCL. You can see that on the same card. The orange bar and the light blue bar basically compare the two different frameworks on the same graphics card. But there's still benefit of using OpenCL over using OpenMP on a CPU. So it's something that we're kind of continuing to develop. And to give you an idea of sort of what a typical workstation might look like, this is a machine that we built at the University of Edinburgh when we were working on the Google project. And before we kind of understood what the performance benefits from the GPU we were going to be, we spec'd this machine pretty highly on the CPU side at the time. So it was a 2-socket 20-core machine with 250 gig of RAM. However, if we were to do this again now, knowing what we know, we would probably reduce that spec and save some money on that side and just focus our money on the GPUs. So we outfitted this machine with a couple of GeForce 1080 CPUs, which at the time I think were about 600 euros each, and a couple of more expensive Titan X GPUs. And the nice thing about this is that you can run 4 models in parallel, one on each GPU at the same time. And the way in which we do that is that we use MPI. So I said earlier, we're not using MPI to do a domain decomposition. We're using MPI basically to farm out individual models to either execute on different CPU nodes, or in the case of GPUs, to farm out those models to each of the GPUs. So I'm just kind of quickly skipping through these last couple of slides because I'm aware that I'm kind of running out of time. But in terms of kind of future work on performance with gprMax, as I said before, I think the biggest thing is getting somebody to do the domain-based decomposition. So that will basically mean that if you do have access to an HPC and you have very, very big models that are never going to fit on a GPU, then you can use MPI to split them across different nodes of your HPC. So that's probably the biggest thing that we're looking at. The OpenCL solver is in the works and may make it into version 4 that's coming this year. And the other thing we want to do, we talked yesterday a lot about subgridding. Now, at the moment, all of that happens on the CPU, but the kind of next logical step for that is to move that onto the GPU as well, which will obviously bring performance benefits. So thank you for listening. And if there are any questions, we can have a look.